Hello, am I audible now? So, first of all, good afternoon, everyone, and my gratitude to Dr. Banshi Sabu sir for inviting me here from Delhi, and a big thank you to all of you who are still here after the lunch session. So, we are going to discuss today something which is actually very much associated with the lunch and the importance of the food that we have. So I'm sure you all think that you are the owner of your body and you are the master. How many of you actually do think that? Yes? So someone has raised the hand actually. But we are not the ones who inhabit our body. We are not the only ones who are inside our body. Our body is inhabited by certain organisms which are even much larger in number. The cells are much larger in number than we ourselves. So we are going to talk today about them. We are going to talk about the gut microbiota. I am very thankful to Dr. Banshi Sabu sir for asking everyone to speak about the history of diabetes, because I always love to start whatever I do new with uh, with an ode to Lord Ganesha. So today I have got this opportunity to do it in a scientific forum as well. So it is considered that Lord Ganesha may perhaps be the first diabetic, because as we know diabetes, as we know metabolic syndrome, we see a number of features. We see the pot belly, and he loves laddu, that is the sweet, which may lead to diabetes. And the shloka here is Gajanan Bhut Gadadi Sevitam Kapit Jambu Phalsar Bhakshitam Uma Sutam Shok Vinashkaram Namami Vigneshwar Pad Panjakam. So we've heard this a number of times. One important thing here is that he is offered jamun and kaf. These in Ayurveda is considered to be treatment for diabetes. Diabetes in ancient India. The oldest references to diabetes go as back as 4500 BC in the Devik Yuga. In Chakradat Rasayan chapter, that is Shloka 195, it is said that Lord Shiva has dictated a formulation for treatment of Prameya, that is diabetes, to his son Lord Ganesha. Another view claims that Lord Ganesha was afflicted by Prameya because of his eating and working habits, like taking lots of sweets we've discussed. And in 4000 BC, it is mentioned in Ayurveda, which is part of the Atharvaveda. In 1500 BC, in Charak Samhita, it is recognized, which is recognized as a complete treatise that deals in extensively etiology, symptomatology, pathology, prognosis, complications, and management of Prameha, that is diabetes. And when you read the excerpts, you would be surprised how in detail it has been mentioned. And over to 10th century BC, when Sushruta Samhita, the 20 different diseases of urine, and Prameya is one of them. So there's Post Samhita and Yoga Ratnakaram, and then there has been gradual growth in knowledge of diabetes till 16th century AD. So this is our ancient system of medicine in Ayurveda. Coming to the current topic, microbiota and diabetes. As I've just discussed, the gut microbiota is a very complex, and it is a very diverse collection of microorganisms. These are different microorganisms, microbes, viruses, protozoa, fungi, but microbes are the predominant of them, and the total cell count is 100 trillion, which is 10 times the number of cells that we have in our body. The total genes of these microbes is about 220 million, which is about 250 times the 22,000 genes that we have as a human body. So there are more genes of microbes in our body. There are more cells of microbes in our body than we ourselves are. And then almost 90% of these microbes are from two phyla, that is Firmicutes, these are the gram-positive ones, and Bacteroidetes, these are the gram-negative ones, and 10% others are distributed among other phyla. So a healthy gut microbiota is the one which is diverse in nature, which has more of healthy and less of pathogenic microbacteria. So what is the role of gut microbacteria in health and disease? Symbiosis, that is when the gut microbiomes, they ferment fiber, which produces beneficial metabolites. They synthesize vitamins, they support immunity, and they support metabolism. In dysbiosis, there's a loss of the beneficial species, and there's an increase in pathogens. This decreases the diversity and and it is linked to chronic diseases, including diabetes. A healthy microbiome has high diversity, rich gene pool, and it is a stable community. The key influences are diet, fiber-rich diet. It nourishes the short chain fatty acid producing bacteria. It maintains the gut barrier integrity. And in genetics, the HLA variants, they alter composition. Early life has a great impact. The mode of delivery, in the vaginal delivery, there is a different predominance of the gut bacteria as compared to the cesarean section. Breastfeeding also has a great impact on the gut microbacteria. So, and it has a positive impact. I hope I'm audible. Okay. So, am I audible now? So the mode of delivery, breastfeeding has great impact on the microbiota. And antibiotics, especially given during the childhood, also have an adverse impact on the gut microbiota. What is very harmful is the dysbiosis. Dysbiosis is the increase in pathogenic microorganisms and decrease in the healthy microorganisms. So now coming to diabetes, the topic today is diabetes and microbiota. So is the pathogenesis of diabetes related to microbiota? Is there any, are there any evidences? Yes. The pathogenesis of diabetes, both type 1 diabetes and type 2 diabetes, has relation to, to microbiota. In type 1 diabetes, we know it is an autoimmune process. It is a T-cell mediated autoimmune process. Here also, microbiota has a role. And type 2 diabetes, we understand, is an inflammatory metabolic dysfunction process. And here also, the microbiota has a role to play. And the central role is that of dysbiosis, that is disharmony. In pathogenesis of type 1 diabetes, autoimmunity, we understand that type 1 diabetes is a T-cell mediated destruction of, in that a T-cell mediated destruction of pancreatic beta cell takes place. There's some studies which have shown that before the onset of the beta cell destruction, there's a change in the microbacteria. There's a predominance in the pathogenic microbacteria. So there are microbial shifts towards decrease in diversity, towards decrease in short chain fatty acid producing microbes, increase in bacteroidetes and pro-inflammatory opportunistic bacteria, and the leaky gut. There's an increase in a protein called zonulin. So this is a protein which increases the size of the distance between the cells in the gut. So which makes it possible for endotoxins, for LPS to pass on into the circulation. So these tight junctions are disrupted by increase in zonulin, and this leads to LPS and antigens crossing the gut barrier, which activates the islet reactive T cells, and ultimately leading to beta cell destruction. So this has been proven by mechanistic studies by blocking zonulin receptor through this FZ1 by O. So this has shown a decrease in type 1 diabetes incidence by 70%, even though this study has been done in rats. And by molecular mimicry also, this plays an important role through the microbiota in development of type 1 diabetes. So I'll move on further. We are running short of time. Pathogenesis of diabetes of type 2 diabetes, dysbiosis, decrease in butyrate producers, decrease in diversity, increase in gram-negative bacteria, leaky gut and metabolic endotoxemia, increased inflammation, leads to increased insulin resistance, and harmful metabolites. So these are the shared features in both type 1 and type 2 diabetes. The role of microbiota and control of glycemia is bidirectional. So both the dysbiosis or derangement in the microbiota leads to poor glycemic control, as well as the poor glycemic control leads to dysbiosis. So I'm just running over the slides because I see we have very little time left. So some beneficial metabolites like short chain fatty acids, butyrate, propionate, acetate, they increase the GLP-1 and PYY. So we use GLP-1 receptor agonists, but these bacteria actually stimulate the release of GLP-1 in our intestines, which has a beneficial effect on control of glycemia. There are certain harmful metabolites like branched chain amino acids, which lead to insulin resistance, which is produced by the Prevotella copri, and TMAO, which worsens tolerance and insulin signaling, and IMP, which impairs insulin signaling via mTOR. So when these are produced in high amounts, that actually leads to poor glycemic control. So there are definitely clinical correlations in both type 1 diabetes and type 2 diabetes. So this is actually a bidirectional process. Is there any relationship between microbiota and complications of diabetes? Yes, there is. So gut microbiota influences long-term progression of diabetes and complication. In CVD, the gut microbiome choline, TMA, and increased atherosclerosis. In CKD, the dysbiosis leads to increase in uremic toxins, inflammation, and nephropathy. Systemic inflammation, that is LPS, TL4 receptors, and this leads to ultimately increase in CRP, IL-6, and rise micro and macrovascular complication. In type 1 diabetes, through a study, it has been shown that decreased microbiome diversity leads to faster decrease in the C-peptide and aggressive autoimmunity. And these are dynamic interactions. We've already talked about, we haven't talked, but drugs have profound effect on the microbiota. So it is considered that the time-tested metformin actually works through the change that it brings about in the gut on the microbiota. The metformin leads to increase in Akkermansia, mucinephilia, and short-chain fatty acid producers, which increases the GLP-1 and improves the glycemic control. Alpha glucosidase inhibitors, they provide more carbs to reach the colon, and they increase the bifidobacterium and lactobacillus. DPP-4 inhibitors, they increase lactobacilli. SGLT2 inhibitors increase the short-chain fatty acids in cecum and increase in Akkermansia. And GLP-1 agonists, they also alter the microbiota, increase in allobaculum and decrease in Prevotella. So there is a convergence, multiple agents enrich Akkermansia and mucinephilia with improved gut barrier and metabolic health. What are the therapeutic interventions which we can use to microbiota? We can use probiotics and symbiotics, which in studies has shown to lead to decrease in CRP, IL-6, TNF alpha, increase in IL-10 and short chain fatty acids. So there have been good results, best results with symbiotics as compared to just probiotics. Fecal microbiota transplantation is quite known. So where a lean donor is used, the fecal mass from a lean donor is transplanted, is given to the recipient, which has shown to increase insulin sensitivity and glucose control. Diet and prebiotics is absolutely essential. This is what we always talk about in lifestyle modification. And the future approaches are bariatric surgery, which also alters the gut flora. So this is an interesting study. It is a small study with only 20 participants, but it has shown that after 12 weeks of fecal microbiota transplantation, 17 individuals have responded with decrease in multiple parameters, with the decrease in HbA1c, with decrease in fasting glucose, with decrease in CRP. But this also has shown one thing, that not everyone responds. Only 17% have responded, 3 have not responded. And this is a meta-analysis of a short term. Short term is 12 weeks here, response to FMT. And as you can see on the all the all the results are beneficial to the left of unity. So this shows that FMT does have a role in achieving glycemic control. In conclusion, the gut microbiota is central player in diabetes pathogenesis, glycemic control, and complications. And dysbiosis leading to leaky gut can cause an autoimmune cascade and lead to type 1 diabetes. Dysbiosis with endotoxemia may lead to chronic inflammation and insulin resistance, ultimately causing type 2 diabetes. Glycemic control, there's a bidirectional relationship. Microbes regulate glucose. Hyperglycemia reshapes microbiota. And drugs, probiotics, symbiotics, FMT, diet and prebiotics, bariatric surgery, and postbiotics. These are the therapeutic options related to microbiota. So targeting microbiota offers a paradigm shift from symptom management to mechanism-based personalized therapy. Thank you.